Okay. Hello, can you hear me?
Yes, sir.
Okay, so do you have any question regarding last lecture? Then we'll start today's class. Last class I was talking about Hamilton's principle, so maybe we can start from there. But before that, let me know if you have any. Okay. So Hamilton's principle, as I mentioned last time, it has two parts. First is that it introduced the concept of Lagrangian. The statement I wrote you that every mechanical system is characterized by a definite function of qi, qi dot and t, that is L qi. I'll mention qi. Sorry, this is not dot. Um, okay, so this is qi dot t. So every mechanical system is characterized by a definite function which is known as the Lagrangian. So first part, so known as Lagrangian. Okay. Second part, so this is first part. Second part of this, that Lagrangian's exact statement, you read it from Goldstein book or some other book, but let me. Second part is that if I define a mathematical quantity, say action, which is some initial time t1 to some final time t2, and this quantity L dqi dot t dt. This is the line integral from time 1 to t1 to t2. This quantity will be extimum. So the system will evolve from one initial time t1 to another time t2 in such a manner that delta I should be 0. So this is the statement of second part of the Hamilton's principle. So Hamilton's principle says there is a Lagrangian for each and every mechanical system, which is function of generalized coordinate, generalized velocity, and time. So dqi is dqi dt. This is the meaning of that. I runs from 1 to s. S is the number of degrees of freedom. Okay. So this part is clear, that what is the statement of Hamilton's principle, and then this quantity which is known as action, its name is action. Action, what is action? Action is nothing but a line integral from initial time to final time of this Lagrangian. Okay, that is action. So action will be extimum. Extimum or means minimum or maximum. So it is a Hamilton's principle of least action. Generally it is minimum, but mathematically one can argue that it can be extimum also. So that is why it's called Hamilton's principle of least action. Okay, so this is the Hamilton's principle of least action. So let me explain the physical meaning. Then we'll find that this condition will give you the equation of motion. So that is the aim of today's class, that will derive this equation of motion. Okay. So we'll first explain the meaning. So generalized coordinate I have introduced. So suppose a system, I have a system whose generalized coordinate are qi. And I didn't mention one thing in the last class, that when I have a Cartesian coordinate, suppose three-dimensional space, so coordinate is x, y, z. Okay, so if this is a Cartesian three-dimensional, if you have a spherical polar coordinate, you can have r, theta, phi. Okay, so if you have three coordinates, it's three-dimensional space. But this is a generalized coordinate, and it depends on degrees of freedom of the system. If you have a 10 degrees of freedom, you will have 10 generalized coordinate. But we can imagine that this generalized coordinate also belongs to some space, some coordinate system. So that space is known as configuration space. So what is configuration space? Another new concept. I have a coordinate system, say all are mutually perpendicular direction. Imagining, you can imagine that, because three mutual perpendicular direction only we can imagine. So suppose this is my q1, this is my q2, this is my q3, this is my q4, this is my q5, this is q6, and so on. So if you have 100 generalized coordinate, you have to imagine a 100-dimensional space which has all the generalized coordinate is one mutually perpendicular direction. Exactly the role of x, y, z. Okay, x, y, z, three mutually perpendicular. It is very easy to visualize that we can have three mutually perpendicular direction in 3 dimensions. Similarly, this configuration space will be the space spanned by the generalized coordinate. So configuration space spanned by the generalized coordinate. So if you have a free rigid body in 3 dimension, the configuration space will be 6 dimensional. If you have 5 particle on a surface plane, 5 point particle on a plane, then its configuration space will be 10, because 5 particle on a plane has 10 degrees of freedom, so its configuration space will be 10. Okay, so any question on this configuration space and statement of the Hamilton's principle? Because now I'll clean this board and we'll proceed further. Okay, so so every system is described by generalized coordinate, right? That means every system is a point in the configuration space. Is that clear?
Okay.
हाँ.
So, हम जिन भी चीज़ों के कांटेक्ट में आते हैं या जो भी मोशन हमें डिस्क्राइब करना होता है, तो उसके लिए तो हमें सिर्फ 3 डायमेंशन का ही काम होगा ना?
हाँ, but I am saying the configuration space. I am imagining a space which has the one, each and every axis is one generalized coordinate. We are assuming this. We are imagining this. You will see immediately advantage of doing that.
So जैसे अगर कोई system
I am not saying that space-time dimension is 3 plus 1. This dimension I am not saying. Then only you can have 3 mutually perpendicular, 3 independent variables. If you have a 3-dimensional space, then you can have only 3 mutually perpendicular, mutually independent variable. But by definition of generalized coordinate, we must have S number of independent coordinates.
So जैसे कभी-कभी ऐसा होता है कि कोई मान लीजिए ऐसा कोई मोशन है जो कि x, y, z और वेलोसिटी, जैसे ये 4 चीजों पे डिपेंड कर रहे हैं, मतलब vx, vy और vz, तो फिर वेलोसिटी के लिए तो हम लोग शायद अलग कोऑर्डिनेट लेते थे ना, उसमें बोलते थे उसको वेलोसिटी स्पेस ऐसे कुछ.
No, that I am not introducing. Velocity space किस purpose में introduce कर रहे, that I don't want to bring here. But I know the generalized coordinate is, if you have system S degrees of freedom, then I can introduce S independent quantity. Now, independent quantity can be assigned with a mutually perpendicular axis. So if I want to imagine, this is imaginary, so no problem with that. I can imagine 100 dimension, I can imagine 1000 dimension, I can imagine anything. But really we have only concept of 3 dimension. But this is a different. I am making a formulation which is that a hypothetical space which is called configuration space, which is the dimension of the configuration space is the same as the number of generalized coordinates. Because generalized coordinates are mutually independent. Mutually independent quantities can be assigned with perpendicular axis, that we know. Here we have 3 independent. So I am okay. So I think that is fine. Now if you have a configuration space, suppose this is my configuration space. So this, any point in this space will be function of q will be the q1, q2. So suppose this is 5 dimensional. So q1, q2, q3, q4, q5. Suppose. So this any point will be q1, q2, q3, q4, q5, right? Any point will be this coordinate. For example, that any point in the 3-dimensional space is the can be represented by some value of x, some value of y, some value of z. So any point will be like this, q1, q2, q3. So suppose I have a initial point. Let me initial time, the system, suppose I have in the initial time. So suppose I have in the initial time, I wrote q, let me write j and I for the initial, or maybe 1 for the initial. Okay, no problem. So let me so let me write q I and initial time this. So any point will be represented by I equal to say 1 to 5 or 1 to s in general. So advantage is that every point on the configuration space represent the system. Is that clear? Every point in the configuration space represent the system at instant of time. So this is suppose an initial instant, so I write. Similarly, this is suppose a final time. So I can represent the system qi 2. Okay, because 1 is for initial time, 2 is for the final time as t1, t2. So this is at t equal to t1. This is at t equal to t2. Now system will go from some initial time to final time. That is the equation of motion. How system will go? That is the equation of motion, right? So in principle, system can go in this by connecting these 2 points in. So system can go in this way. It can follow this path. It can follow this path. It can follow this path. So system can evolve in infinitely many ways. Is that fine? Because 2 points can be connected by infinitely many ways. So in the configuration space, system from initial time t1 to final time t2 will evolve in infinitely many ways. Okay, is that clear? If you have doubt, please ask in this. Idea is that you can go from in 3-dimensional. Suppose if you any idea, any confusion, think of in. So what I'm saying is that from your hostel to department, how many routes is possible? That I am asking. That is in 3-dimensional space. Now in the system has a much more degrees of freedom. So I am imagining a generalized coordinate, and generalized coordinate will be construct a configuration space, and configuration space has every point is the system. So one point to another point, system will go in infinitely many ways. Okay, is that clear? But Hamilton's principle says, so you can calculate your action. Suppose this action I1, you can calculate your action I2. This is your I3. Action means that line integral T1 to T2. This is your action L, Qi dot and T dt. So this you can calculate. Line integral, you are familiar with the line integral. Vector calculus you have studied. So you can go from here to here infinitely many ways. So so you can have I. So this set will be infinitely many. Now Hamilton's principle says that system will choose that path where delta I among all these paths will be 0. That is the Hamilton's principle. So I think explanation of Hamilton's principle is clear to everybody. So system can go infinitely many ways from initial time to final time. System can evolve infinitely many ways. And also this path, concept of path you have understood in thermodynamics. Similar thing you have used in thermodynamics. So each path, this line integral will have a different value. So I can have I1, I2, I3 to infinity because there are infinity paths. For example, I is suppose your cost from your hostel to the department, the traveling cost. Now you can go by a rickshaw to Lanka and then Lanka to department by rickshaw, then it will have a different cost. You can have without any vehicle, you can go from your hostel to the department, 0 cost. You can go by some Ola bike, it will take some rupees, it has another cost. So action is like a similar analogy to the cost. Now you may prefer that you will go to the department in minimum cost. If you decide, then the path is fixed, that okay, then you have to go this. If somebody wants to define that okay, he wants to go to the department in the shortest time, in 2 minutes he wants to go. So then action is like the time taken, right? So action has that role. So now Hamilton's principle says that action, that like a time taken or cost kind of thing, will be minimum or maximum, extremum. So delta I. So that will give you the equation. Any question? I'll now derive equation of motion from it. But to derive equation of motion, we need little bit knowledge of variation of variational principle, which you must have studied in your 3rd or 4th semester, I don't know, in mathematical course, I think. Every year student used to say
No,
that.
sir.
Okay, so let me give you some small introduction of variational principle. So suppose I have a quantity, a function f, which is y dot, and function of x. And I want to calculate a quantity, say j, let me write j, which is the integration of this quantity. Suppose I am just considering an example of variational principle which will be directly relevant to our problem of least action. So this we want to calculate, and we want to extremize this using variational principle. Okay. So now this will calculate that this quantity in different path. So path is y path. Let me define path is y equal to x. This is the path, and suppose at x1 and x2 point. So corresponding y values are y1 to y2. So you want to go from x1 y1 to x2 y2, and suppose this is in a 3-dimensional, it is in a plane, xy plane. So this is in xy plane. And I want to calculate this quantity and want to see that how this quantity changes, j changes with different path. So in xy plane, this is x1, x1, y1, and suppose this is x2, y2. I can have different path, infinitely many path, because I can connect these 2 points infinitely many ways. So I'll try to see, and these are different paths. This is path 1, this is path 2, this is path 3, path 4, path 5, to infinity path. So I'll show you that this path, infinitely many path, I'll try to calculate this quantity. So how I vary the path? So I have to introduce some parameter. So let us I use a parameter alpha such that y is function of x and alpha. So for different value of alpha, I'll have different path. So to changes from one path to another path, I introduce a parameter alpha. So alpha parameter is introduced to change the paths. Okay. So this, and I can write that this variation as let me I can have a Taylor series and expansion kind of thing. So y at x0 plus some alpha, then derivative of y, let us write that eta of x. Okay. So I make a expansion, and we are considering alpha to be small parameter, such that this will be a good approximation. So variation, or you can think of that alpha is not small, but I can think of that variation I make in this way. This is one proper way of assuming that this y alpha is related to y at alpha equal to 0 times alpha times some function eta x. It may not be, it will be Taylor series kind of, but may not be Taylor series. If you have to make a Taylor series, then you have to small alpha, then it will have a value. But we are not necessary to assume that it is Taylor. I am introducing a parameter alpha such that for different values of alpha, I can take a different path. And I introduce alpha in this manner. So now your j is function of alpha, right? Because this is now I am integrating from x1 to x2, and y is function of x and alpha. Y dot is also function of x and alpha, but x is not function. Okay, so this is the f, and then you have dx. So this is the quantity. And now to make a among this, which will be the which will correspond to the minimum value we are interested, minimum value of j alpha you are interested. So this implies that dj alpha d alpha, because this is the parameter which changes the path, right, should be 0. This will be the condition that you know minimum or maximum condition is that. This is also equivalent to say that this quantity has a stationary value. I'll explain that. See, when you plot something like this, suppose, so this has a this function, I'm not doing a sine function, suppose arbitrary function. Here it has a minima, here it has a maxima, maybe here another maxima, but where minima or maxima will occur, the slope will be flat, horizontal. So that is the stationary, that means value is not changing. Slope is horizontal to x-axis, that means value is not changing. So that is why I call that at the minimum value or maximum value, this function has a stationary value. Okay, but this doesn't matter. We don't need, we only need that condition for where this j alpha will be minimum or maximum. So this is I'm doing in general, and we'll find that it will be useful to find the equation motion using Hamilton's principle of least action. Okay, so unfortunately I have to erase now, but now you have to remember at least two equations, y and j alpha.
Sir,
Okay.
can you please explain that equation yx alpha equals to yx 0?
We are taking like that. See, alpha is introduced to go from one path to another path. Okay, so suppose alpha equal to okay, I'll explain. Alpha will take values. Okay, so now, so alpha, so when alpha equal to alpha 1, suppose this path here to here. When, so this is alpha equal to alpha 1. Now alpha equal to this path, I say alpha equal to alpha 2, and so on. So different value of that. Now I am saying that, okay, if we don't introduce alpha, so at alpha equal to 0, then this will satisfy that y alpha equal to 0, that means x of 0. So this satisfy this equation. Now when alpha not equal to 0, I am multiplying that by a function. This is also, I should mention, regular what is the word I should use? Not only regular, but regular function. Regular function means no singularity. Singularity, you know, right? Diverging, that in nowhere it will be infinite. Continuous in mathematical language, continuous function. So I, to make a variation of the path, I just introduce like this. But this equation also you can think of as a analogy of Taylor series expansion. When alpha equal to more, then this has the first order approximation. Okay. So let me now. So if I, this eraser is stupid. So I don't have to lift my pen. Okay. And when I lift my pen, eraser will stop. I see. Okay. So now let us calculate this quantity from here. So d, what happened? dj d alpha, and it is integration x1 to x2. So it has function depend on y depend on alpha. So if I make it this, so del f del y, then del y del alpha, differentiation chain rule, right? Then we can have del alpha f changes y dot, then del y dot del alpha, right? And x does not change with depend on alpha according to our consideration. So this times dx, okay, and this will be 0. Right hand side is 0. Okay. So now I can I forgot to say one thing. Y dot here, y dot is del y dy dx, or del y del x. Del, it will be better to write del, because now y is function of two variables. Here there is no time, right? Here only when we consider variational in the plane, we have x and y. Okay. So y dot is your del dot, means here when we consider the actual classical mechanics problem, then time will come, but here it is y dot is del y del x. So let me put that here. So this term will be changed to del f del y dot. Now y dot is del y, so it will be del 2 y del x del alpha. Okay, this term will change. Fine. Okay, I can write this. Let me clean now. Remember this, I'll need this equation. It is like a blackboard, right? You have to erase something and you have to write. I can keep, but this is better for me. You don't have to go next page. Okay. I'll keep this term as it is. All of you are familiar with this is integration with respect to ds, and you are familiar with the by parts integration. Integration by parts. Integration by parts with respect to x, and keeping this as a first function and this part is second function. So this quantity, let us x1 to x2, first term will be as it is, del f del y del x alpha as it is. Second term, okay, let me write dx, then plus. Now I'll do by parts. So first function unchanged, del f del y dot, and if I integrate this integration of second function, then integration of second function with respect to x will give you del y del alpha, right? And this can be calculated at x1 and x2. Okay, then minus derivative of the first function, so derivative with respect to x. So or I can write ddx or del x depending on how many variables. So let me write variation. So it will del x of del f del y dot. Okay, and then integration of first function. Integration of first function del y del alpha, and this is again integrating over dx. x1 to x2. Fine. Remember, right hand side is our 0. I am not writing, but we have to. Now I am going to tell you that this quantity is equal to 0. That I am going to explain. Listen carefully. So when I consider, I am calculating that j which is function of y alpha, and when it will be minimum or maximum, extremum. Okay. So that we are calculating. So in the when we are calculating this, then between the different paths, so paths are from x1 y1 to x2 y2. These are the path between 2 points, right? So these are the path. So variation of y at the initial point and final point at 0. So basically delta y, the variation at x equal to x1 is 0. This is 0, no variation. Variation starts from here, variation ends here. So two terminal points, the variation is 0. So this del y del alpha, variation with respect to parameter at x1 equal to 0, x2 equal to 0. So both upper limit and lower limit, this function is 0. So this quantity is 0. So now we have two terms, x1 minus x2, del f del y del alpha minus del x of del f del y dot and del y del alpha times dx. Now remember our y equation, y x alpha was y x0, no alpha term, plus alpha times eta xy term. So del y del alpha will be eta x, which we have taken a regular function, non-singular function. There is no singularity, continuous function. Everywhere it is continuous. There is no discontinuity. Nowhere it becomes divergent. Okay. So this quantity I can take common from both places, from here and from here. Okay. And that I replace by eta. Okay. So let me come in the top. Okay. So what we'll have now, integration x1 to x2. So this is your j alpha d alpha quantity is del f del y minus del x of del f del y dot, and this quantity is multiplied by a regular function eta, then you have dx equal to 0. Okay. Now, if this is if you have an integration where say mx eta x, and this integration between some point x1 to x2 is 0, and if eta is a regular function that I said non-singular continuous function, then m is 0. M has to 0. If it is a continuous function, regular function, no singularity, then this is a mathematical result which I am not going to prove, but you can take is granted that this. So this implies that J path for which J alpha will be minimum or maximum will satisfy this condition. I'll consider one example, then the variational principle will be very clear. But this is just an example of variational principle. I'm not teaching you the details of variational principle. Then major part of the classical mechanics course will be cannot be covered. Okay. So that is why. But if you actually in those who have mathematics as a minor subject may have done this variational principle. It is there in your syllabus, but I don't know. I get only information from the students. But anyhow, so this is so if this will be extremum only when this condition is satisfied. This is an example. Now I'll consider how this variational principle is useful. You can get a flavor once I consider this example. You can realize this, you can get a flavor of this, what is going on. See, suppose I consider a plane. Okay. So plane means xy, and then I'm saying in the plane there are many paths, between 2 points. So let me consider this is a plane, xy plane, and between these 2 points x1 to x2 there are many paths. Okay, many paths, 1, 2, 3 I wrote. Which path will correspond to the minimum distance? So now question is that which path will correspond to minimum distance? And you have to solve this problem. Answer you all know that straight line path will follow the minimum distance. If I go straight line path, then it will be the minimum distance, that we all know. But whether that result, this known result, can we prove using the mathematical variation of this variational calculus? So the distance you all know, distance between 2 points is basically ds is root over of dx square. I'm writing in a variable form. You know, distance between 2 points is distance between 2 point x1 x2 sorry x1 y1 and 2 x2 y2 is x2 minus x1 whole square plus y2 minus y1 whole square and this square. So if the distance between xy and a point x plus dx, y plus dy point will be this. Because when you do the thing that we had infinite decimal changes to that way. So this quantity you can write this. So this quantity, So when this quantity will be, so action you can write, and so then let me write this in a little bit simplified form. So now the distance, now your action will give you the total distance. Total distance will be this element times x1 to x2, and under which condition the total distance will be minimum, that we are going to find. So this will be your ds. So now this I can write as x1 x2. This is elementary distance. Elementary distance I integrate to get a total distance. Okay, good. So this will be your dx square plus dy square, and that you'll have to integrate. Okay. So this you can like this form, x1 to x2 integration 1 plus say y dot square dx. Y dot means here dy dx. Here y is only function of x, so I use total derivative. When y is more than one variable function, then you should write partial derivative. So y dot is this, so y dot square dx. Now, so this quantity is like your f. Now I want to see whether this condition gives the minimum condition or not. So this is like your f, but fortunately this f is now function of only y dot, nothing else. So for this simple case, it is only function of y dot, no y dependence. So now this condition means what? You can directly minimize, etc. You can do, but I just want to do with this condition. So now if I apply this condition, so if I apply this condition, so del if this is your f, so del f del y, how much we have 10-15 minutes, equal to 0, and then this condition. So this condition it says del x of del f del y dot. So f is root over 1 plus y dot square. So del f del y dot will be 1 over dot square, because half times this, and then so half 2, then 2 y dot, right? This is the derivative. So half and 2, this will cancel. So this y dot by root over 1 plus y dot square, this will be 0 from this condition. ddx, this is 0, minus right hand side is 0, so minus gone. So this quantity is 0. That means y dot by root over 1 plus y dot square should be constant. So see, okay, we have to come back to Hamilton's principle today before we end the class. So that is why okay, with this example, then we'll go directly to the Hamilton's principle and derive. Okay, this is constant, so you can write this is constant. That means y dot will be constant, right? You can see easily y dot square equal to plus 1 plus y dot square equal to c square. Then take all y dot this side, then you'll find that y dot equal to constant. So y should be this is constant. So maybe other constant. So let me write a. So y dot is constant. So y is ax plus b. Right? If y dot equal to constant, that means y equal to ax plus b, which is the equation of straight line. So we proved that in a plane, the path corresponding to shortest distance is a straight line. Okay, so I can design many other problems in Goldstein book also. There are problems. So there are many paths y as a function of x, but if you go with the minimum distance path, then it has to be straight line. Okay, so this is a mathematical. All these I did mathematical. Next 10 minutes, now I'll go back to the Hamilton's principle and we'll see what will be the equation of motion. Okay, so let us go to our action. Directly we can go to action and we'll see that using the variational principle, what will be the condition. Sujit Kumar Saigal is tell me that he will not be allowed in my class anymore. Okay, so now we'll go to the Hamilton's principle. So Hamilton's principle, we had the action. Action was that it is Lagrangian, and let us assume 1 degrees of freedom. So Q dot and T dt. So T1 to T2. So now I'll write delta I. This is the Hamilton's. It will be the extremum condition. So this what we'll write T1 to T2 del L del Q delta of Q. I'm taking variation now, not like that variational principle. I had one parameter and changing with that parameter. Now I'm considering in terms of variation. So here we had dy d alpha, but it is the so differentiation Lagrangian with respect to Q, then variation of Q, plus differentiation of Lagrangian with respect to Q dot, then variational of Q dot. Okay. Okay. And then now Q dot is ddt of delta Q. Okay. Q dot means. So that we can write. So this quantity should be 0. So T1 to T2 del L del Q delta Q plus del L del Q dot, then ddt of delta Q, and whole thing is integrated over dt. Now again we'll do the bypass integration here. This part will keep as it is. So if we bypass integration, because this is a ddt of something, and also remember del variation of Q at T1 equal to 0 equal to delta Q at T2, because Q does not change, generalized coordinates does not change at the point, initial point and the final point, because where system is starting and where system is ending up. So again, if you do the bypass integration, so this will be T1 to T2, then del L del Q, and this term you will get ddt of del L del Q dot, and whole thing is multiplied by delta Q, then dt equal to 0. I have not done one step here. You do the bypass integration, the middle term again will vanish, and after vanishing middle term, you'll get this. Middle term vanish because of this initial condition. Okay. So now go up, and we'll see the equation of motion. And naturally, this is now dq is the variation of that. We are assuming to be a continuous function, and we'll have this integrand inside this bracket will be 0. So we obtain the equation of motion del L del Q minus ddt of del L del Q dot equal to 0. So system will go from initial time to final time in such a manner the Lagrangian will satisfy this, which is known as equation of motion and also known as Euler-Lagrange equation. See, this is Lagrange, scientist name, Euler, scientist name, Lagrangian, L is Lagrangian. So student confuse and write Smith's spelling. Lagrange is scientist name, so this is known as Euler-Lagrange equation. Okay, so quickly we'll practice this equation. We have 5 minutes time. We can quickly practice this equation and we'll see. Suppose I give a Lagrangian like this. Suppose I give a Lagrangian like this. L, say x dot. Okay, so suppose there is no explicit time. So half m x dot square minus half k x square. So quickly find the equation of motion. Okay, find in your copy the equation of motion. Are you doing in your calculation, Shruti?
Yes, sir.
Quickly you do this that equation of motion and find that if the Lagrangian is like this, then what will be the equation of motion. But we later will teach you how to find a Lagrangian of a system.
Sir, mx double dot is equal to minus kx.
Mx double dot
Is equal to minus kx.
This is the, do you know this equation?
Yes, sir, simple harmonic motion.
This is a mass spring system or simple harmonic system. So x double dot plus omega square x equal to 0, where omega square is k by m. Okay, so everybody should do this. You first find del L del x. Here q is x. Q is here q is like x. Q dot is like x dot. So you can immediately find, and then so if I have a, immediately we understand that a simple harmonic oscillator, this is a equation of simple harmonic oscillator. This simple harmonic oscillator has a Lagrangian of this kind. So now if you can find Lagrangian of a system, then half of the classical mechanics you have learned. So now we will spend some time to find how to find the Lagrangian of a system. And to find that, first we should learn few properties of Lagrangian. So let us quickly go through in 4 minutes properties of Lagrangian. Okay. If L equal to some constant times L, then equation motion will change or not? There are two Lagrangian. One Lagrangian is L prime, another Lagrangian.
No, sir.
It will not change because this also multiplied by C, this also will multiplied by C, and right hand side is 0. I take C common, so it will not. So two Lagrangian, so any Lagrangian you multiply by a constant, dynamics will not change. What will happen? Your path will be shifted. All path will be shifted, but shortest path will be there, shortest path, or minimum cost path will be there as minimum cost path. All will change. Similarly, too, second thing is that if your L prime is L plus C, equation motion will change. Again, no.
No, sir.
Because equation motion always have a differentiation of L, and differentiation of a constant is always 0. So if you add something to your equation, constant, if you add a constant to the equation Lagrangian, equation will not change. If you multiply with a constant, equation will not. So two properties very quickly we have learned. So let me see more properties we can learn. Yeah, one more property sure we can learn. Okay, so let me one more property. Suppose if you have your L prime Okay. Suppose I have system A, which is described by Lagrangian A. I have another system, which is system B, Lagrangian, described by Lagrangian B. And this system is not talking to this system. They are not interacting. Talking means they are not interacting. So this is the independent system, this is an independent system. So total Lagrangian of this total system will be L equal to LA plus LB. So if you have two systems which are not interacting each other, their sum, the sum of their Lagrangian will be the Lagrangian of the final system. Now suppose I have a system, another system. So this, let me write with blue. So system with blue, and this is system with red, but they have interacting. So in that case, total Lagrangian will be Lagrangian of A plus Lagrangian of B plus, because they are interacting, so there will be a interacting Lagrangian. So this is another properties of the Lagrangian. So three properties we have learned. Two is multiplied by constant, equation motion will not change. Adding a constant, equation motion will not change. If I have a independent system, then I can add their independent Lagrangian to get a final Lagrangian. So suppose I have two free particle. This particle is not bothering this particle is not bothering this particle. So they are free. So I'll find Lagrangian of first particle plus Lagrangian of second particle. Then the Lagrangian for these two particles will be L1 plus L2. This is a very simple but very, very helpful properties. When we will calculate Lagrangian of three particles, four particles, so we'll try to calculate with Lagrangian over individual particles, and then we'll add them up. Okay, maybe you may have another class, so I'll stop here. If you have anybody has quick question, other people can leave and join other classes. Those who have question, you can stay for a few minutes and then I'll leave. So maybe I am stop recording. It doesn't seems that anybody has any question, but read it. And also I'll discuss in your group. I need two classes every week. See, one class, and then I'm also forgetting where I stop. You people also forgetting. So to have a continuity, I must have two classes. Either Krista will give me that class on Friday, or I'll try to find some other time when I can have your class. Okay, bye then.